Okay, so our next speaker is Marc Toussaint. Hi, Marc.
Hi.
Hi.
Does the sound okay?
Yes, sounds good.
Okay, cool.
So let me give you a super brief intro. So Marc studied mathematics and physics, right? I got that
That's
right.
right.
And and then he started to research on neural networks during his PhD. He has been postdoc in Edinburgh. He's a researcher at Honda, then a researcher at the University, TU University, Freie University, professor at Stuttgart, visiting researcher at Amazon, a visiting researcher at MIT, and now professor at my alma mater, TU Berlin. Very fresh, I think. Um,
Yeah.
yeah, so I had the very, very pleasure to work with Marc, which was a lot of fun, and he can really go from high level to very low level mathematical details, and I learned a lot. So I'm really excited to listen to his talk today. And
Thanks. Thanks. Very nice introduction. Also, thanks very much for inviting me to give this talk. That's actually quite a cool topic. Yeah. So let me share a screen, right?
yes, please.
Does that work? Everybody sees that?
Yes.
Okay. So today I would like to talk about physical manipulation planning and learning. And let me actually go to the outline right away. So in the past a couple of years, 2-3 years or so, I've been working quite a bit on what one could call physical reasoning or methods that are about planning and reasoning. And I think I learned a lot actually from these things. And I will talk about one piece of work here first, a technical piece of work, which is about the question of how should you actually describe physics? That is, how should you set up the equations of physics that you use in order to do physical reasoning? And that's only about reasoning and planning. But then in the second part, I'm going to talk about another technical piece of work that we've done recently, which is about learning and then learning in that same framework, learning to reason actually much faster. And then I'm going to conclude with a quick discussion. So let me go ahead with the first technical part. So this is some work that we did published earlier, actually 2 years ago at RSS, which is about using what I call logic geometric programming. You will see that equation also later again, to do physical reasoning or sequential manipulation planning. And I think, so to me, that kind of work was exciting. I was actually focusing on that kind of work a lot also when I stayed at MIT and got a lot of collaborations. So that's why this is also collaborations with Josh Tenenbaum. And I think I learned actually a lot from that. But now let me talk about the points of critique that I typically get when I present this. I think a major point of critique that people, oh, this is a funny example, ask me offline why this is doing this. A major point of critique that I often get is in this work we had to define logic. That's a pain. Jeanette said this yesterday also. And we also had to define certain abstractions of interaction like stable grasps and pushes and simplified pushes and things like that. And the typical thing that people ask me is where would you get these symbols from and where would you get these primitives, the action primitives actually from for this kind of work. And this is actually which led me to think about this. So, and there is different routes. There is one route where you could say, oh, we're going to learn all of these primitives. That's fine. But for me, actually, also to learn more about the fundamentals, I also wanted to understand, like, would there be like a more fundamental level on which we could describe equations and physics for reasoning that are sufficient for any kind of general purpose reasoning? So the question is a bit like, what would be a more fundamental description other than this enumeration of possible, you can grasp this, you can place this, you can push this, as I did in the previous work. And eventually, what I'm going to present is not really novel. The point is, I took that same kind of framework that I presented before at RSS, but kind of thought about what is the most fundamental kind of action and interaction that it could do. And that's, of course, force-based interaction. And people have done this before. Mordash and Todorov, great paper, contact invariant optimization, and also Posa and Ted. Oh, sorry about misspelling here, Tedrake, formulated these kind of path optimization, which are fundamentally described in terms of force exchange. They all have some kind of limitations. So this one in particular has quite some limitations that we could not deal with. And here there were also limitations in terms of what geometry, contact geometries, so could be described. But in particular, something that I was interested in is, does it not make sense to allow something that I call multiphysics descriptions? And that term, multiphysics descriptions, actually also comes from numerical sciences, but I used it in that piece of work here. And basically it means that it seems natural to describe physics on many levels. We do this all the time. Like we describe physics on a level of quantum physics, or of the level of Newtonian physics, or like on the level, like naive physics that people on the street actually use physics. All of these are very different descriptions, or porous material physics, or things like that. So also in science, we have so many descriptions actually of physics, and we use, depending on when and where and which component of physics in our world we want to describe and reason with, we use different models. And I find this actually quite interesting. So in numerical science, the terms are actually also used for that. Multiphysics, meaning, for instance, when you numerically simulate a physical system, fluid system or something, then you use actually different parts of physics to describe different components, maybe the one using fluid dynamics, the other electromagnetic interactions and things like that. And here, what I kind of propose is to allow in a physical reasoning framework or path interaction, like path optimization framework, to use different levels of descriptions to actually do the reasoning on that level. And I think that's kind of natural, and we should try to do that. And essentially, what is going to happen is we describe physics as if it would switch, as if it sometimes applies Newtonian or Newton-Euler equations on that object, but sometimes the physics applies just the static placement equations on some other objects and things like that. Okay. So let me describe this technically and show some results, and then later discuss again on a higher level what we learned. Technically, we describe the problem as a path optimization problem, so which means we try to find a path of the world, actually, not only of the robot, but of all objects in that scene, which respects physics constraints. And all of this is here like equality constraints on the path and kind of transition constraints when different equations actually modes switch between things. So the details are not so important, but the point is that we actually describe the problem as path optimization problem. We want to find a realistic path of the future of all objects subject to some physics constraints. And which constraints exactly hold, this is being governed by discrete decisions, by these kinds of modes. And previously I had kind of like these kind of pick and place kind of modes, and now what I'm going to present essentially is other kinds of modes which are fundamentally about force exchange. And to be clear, again, like how do we describe that path? Well, the decision variables of that path in every time slice are the robot degrees of freedom. That's clear. It's the degrees of freedom of all objects. So the pose is there. It's the degrees of freedom of all force interactions. And of course, they're not independent, but we introduce them as independent degrees of freedom and then use equality constraints to make things consistent. And it's also actually timing. So for these physics equations, we actually also have to co-optimize the timing of every time slice. And that's the technical detail. So what are actually the specific models that we use? There is two technical now pieces actually for that work to actually get it going and get it efficient. So one thing is similar to how we did it before. We use, the setup is that one series of logic decisions, which we call a skeleton. This skeleton decides on which equations govern which objects, essentially. That's basically what I described. They actually also govern which degrees of freedom are created in the process, in the path optimization process. So, for instance, when some object is being thrown or so, it becomes free, and then it actually creates the degrees of freedom for that object to be free. Or if some contact is being established, then it creates the degrees of freedom to represent the force interactions between these two objects. And now what concrete equations basically do we allow this logic to impose on our situation? Well, we have 3 different force exchange models. And the most general fundamental one is the general complementarity contact, just like POSA essentially. I'll explain it in a second. And then some simplifications on that. Namely, to say it's not complementarity, but actually the logic says it's forced. So you need to have contact. So we constrain really the distance to be 0. Further like simplification, it's forced contact, but it's just instantaneous. So it's actually an impulse exchange. And then we have 3 different types of equations that can be imposed on the like objects themselves. And the most general one, again, is the Newton-Euler equation for some arbitrary collection of forces that the force exchanges exert on that object. And simplifications is the logic can decide to simplify the equation to only quasi-static equations, or to simplify the equations even to static relations like static graphs or static placements, things like that. And the point is that we can like integrate all of these different, which equations govern which objects into a single path optimization formulation. And the last technical point of view that actually was crucial, but this almost goes like down levels of coding. A real major pain in all of this is always to deal robustly with switching contact geometries when doing path optimization through contacts. Maybe some of you that technically worked with that actually noticed that. But we had to solve this, no way around. Otherwise, the optimization solvers were not robust. So just a detail on that. So the wrench exchange between 2 objects when they are in contact could be naively be represented just by the force and the torque between the 2 objects. But it turned out, and it took a while to figure this, it's much more convenient as a parameterization for the optimizer to instead parameterize it in terms of the force and what we call the point of attack. And that's obvious, that's one-to-one because there is a direct relation between torque and point of attack and force. But it's only one-to-one when the force is actually non-zero. But it turns out that using the point of attack, everything becomes numerically much more stable, and also the complementarities actually can be described more easily. So the point of attack is actually a point which can fly around in space. And it's the point, like the 0 moment point, which via which the 2 pieces, the 2 objects exert their forces. And naively, it can fly around anywhere in space, in free space. But of course, if the force is really non-zero, then it must not be in free space, but it must be on the surfaces, on both surfaces, right? Only if the objects really have contact, then they can really exert the force. And so you can formulate the complementarity constraints in terms of, either the forces are 0 and then the point might be anywhere. It's just, meaningless, or the force is non-zero and then the distance to the surfaces need to be 0. And yeah, that's the complementarities. And the nice thing about this that this can really nicely handle is switching of contact geometries, point-to-point, point-to-line, and things like that. And there's also previous work on this, the equivalent contact point. Yeah, but this formulation is just a bit different. Okay, this was a technical thing, but it actually, these are the details that actually make it work, I must admit. So let me start a demo, like little demo videos. This is little ball hopping, not very impressive. But what you see actually here is just the result of path optimization. So in all the videos, you never see a physical simulator simulating something forward. You only see a computed path. And if you look at that path and believe it looks quite physical, then actually, yes. So this thing is only being computed as the optimum of these equations. No physical simulator running or so, okay? So we can describe physically correct paths with only these equations. And there is another example, and the point here is you see the point of contact is actually being optimized to actually exert the right forces. And here also the point of attack is actually being optimized to be at the right places, and it can like really do transitions between contact geometries. This is all passive. There's not really anything interesting going on in here. This is a bit more involved. So here the goal is for that thing to get into the green target region. And this is an example push where it actually, realizes it can take a stick and then it figures out where to establish all of these contacts in order to actually get this going. Or here, like this is a free-flying robot, has a bit more options. And it figures out quite elaborate actually placements of points of attacks which actually solve that problem. Some more examples. So it's quite, the optimizer has many local optima, I must admit. On the positive side of that is you also actually discover a whole lot of different strategies to get the task going. All of these are local optima, very different strategies to actually get the box into the placement, and very elaborate ways to actually establish the points of attacks and so on. Here's another one. The goal is for this box to end up on the green table, and it figures that it can use a stick to establish a contact point, like a point of attack, which is, you know, within that little ring there. That thing alone, you know, this reasoning to say, okay, the object has to end up on the table. The only way that it can end up in the table is by going up first. And the only way to make it go up first is to establish a point of contact from below. That's easy reasoning for us, right? But it's kind of like the mathematical program that figured out that it needs to establish like a point of attack from below, and therefore like use the stick to go inside in there. And it's the optimizer actually figuring this out. A point of critique of Rivios actually said that this also does not look very robust, and that's true. It's only a path optimization, and it's like on the edge of what would be possible. So it needs a lot of friction to not slip away here, and that's true. So it's not actually optimized for robustness, but it is correct. And this is Alberto Rodriguez once was talking about getting a book from a shelf, and this is just like one instance of that. Okay, checking time, looks good. So this is the work that, you know, was a bit more recent, kind of an update of our work that we did earlier. And the attempt of this work was to think about what would be the most fundamental level, the lowest level on which we would want to reason or do general purpose physical manipulation reasoning. Some would still say this is an overstatement. It could be much more fundamental. We didn't consider non-rigid objects. So maybe one could make it more fundamental and then doing particle-based things like that. So, okay. But talking about Newtonian physics and kind of rigid objects, that's kind of like, I think, a rather fundamental level to do physical reasoning. And we learned a lot from that, I think, in many ways. But it is, of course, limited. That kind of like, you know, reasoning and finding these sequences still is computationally hard, takes like 10 to 40 seconds to get these full paths. Might be okay, but it's not something that you want to like do on the robot directly. And I think it's also naive. We tried this and we thought about this to believe you just turn this into model predictive control and everything is good. That's sometimes often like a belief. Once you have a planning method, trajectory planning method, you make it model predictive control and all is good. Yeah, I'm not so convinced anymore about that. And it does have local optima, although we do interesting like work on this now also. To actually leverage interesting sampling methods in combination with optimizers. And also in that case, actually we didn't really search over, we could have, but we didn't really search over skeletons just because the runtime would have been rather large. The point is a bit, now why do we actually do this research? Let me first make a general point, and then the concrete point is that we're going to use it to actually generate data. The general point is like, I think in AI research, it's almost a tradition that very often people first try to analytically describe and understand the problem. Like they introduce things like Markov decision processes or Monte Carlo tree search or things like that. And then, but what is really valuable about this, trying to really first analytically understand the problem, is that this framework that is established with them then very often becomes like the framework to do learning inside. So once you understand that you can formalize problems as Markov decision processes, then, well, you maybe can understand that you can also do reinforcement learning and how to formalize it, right? Or if you understand that you can solve like games with Monte Carlo tree search and these very basic things, then you understand, oh yeah, let me learn the heuristic and you get AlphaGo, something like that. And so I think it's really valuable actually to think and try to understand also analytically the structure of these kinds of problems. And based on that, actually then have much more interesting approaches to incorporate learning. So that's really a meta comment of mine. I'm going to like comment on this also later in the discussion. And a bit more concretely, I think it's too, if you, so Chris Atkinson, if he would be here, I don't know if he's in the audience, he would immediately say, all of this is not going to work. You cannot execute this in the real world. It's just a simulation. And he might be right, but I think it's short-sighted to say you only did path optimization and it's not going to work in the real world. Well, the point is maybe not to execute these paths literally in the real world. The point of these methods is first to generate data, I'm going to talk about this, but also to be actually a guide of what can in principle be achieved. So these solutions here, they can function as or serve as reward functions for learning to do the same thing. They can serve as exploration tool as in guided policy search to actually train policies to try to do similar things, right? So in this sense, I think the role of all of this reasoning is, should be thought of much more in this sense. Okay, but yes, we can also like generate lots of data of solutions in different scenes in simulation, and then try to learn actually from that kind of data. So let me transition to learn. And this is a bit shameless. I'm kind of advertising a paper here at RSS. It's paper number 3. It's, the first author is Danny and also Toussaint. Both of them were also co-authors on the work that I just presented. Actually, have this paper here at RSS. So the goal here is to actually now devise systems that look into the scene with a camera and then instantly say, yeah, that's the kind of things I can do in that scene. So we kind of envision that you have the system, it's just camera rigged, and it instantly says, okay, given that scene and given that goal, well, you could try to touch this, then here, then there, and then there, and that might work. Or you could try to predict immediately like the sequence of interactions that looks promising in that scene, purely from vision. And I think that's a completely different, perspective than what we had before, where we first, everything is model-based planning, and we would have to retrieve the shapes and do precise scene modeling and stuff. No, this is really different. We just get an image and then predict like action sequences. And to be more precise, what actually the paper does is it trains a very strong heuristic in the like literal sense of the word heuristic in AI over discrete sequences. But it's so strong that typically the very first sequence that this model actually predicts is already like the right one. But this model should actually also generalize, as our planner actually generalized. This model should also generalize in the first order logic sense, that is, it should generalize across objects. So if there's multiple objects, it should not only apply to one particular thing. So we have to set up a model that actually accounts for that. Just as an example, like the kind of test example that Danny uses in that paper is things like this, where there might be multiple objects, and it's actually a simple task where this object has to end up on that red spot over here. But in order for that object to end up at the red spot over here, you first have to remove the blue block. It's a typical task and motion planning problem, right? But the combinatorics of that one can get really large if you model it on a fundamental level. So here, it's actually very, the tree of possible decisions becomes really large with just 6 actions in a sense. And doing this planning on the fly would be not fun. And that's why, we try to train a neural network as a shortcut. So how can this work? Well, we use the fundamental planner offline to create a large data set of scenes and situations. And in these scenes and situations, do the computationally heavy planning using the methods that I described before. And we get the following data. We get data about in a certain scene, as is just a placeholder actually for scene. And for a given goal, if you tried executing that sequence of actions, and that's in our case like the skeleton that I described before, did the mathematical program end up feasible? Like, did it actually find a path? And we do this like for many, many scenes, many, many different goals, and with many, many action sequences. All of this data actually is generated during tree search of the original planner, but we also vary scenes and goals a lot. So that's the raw data that we actually collect by doing solving many, many planning problems offline. But then the data that we want to use for training is actually sequence data. Why we want to train a sequence predictor, like an RNN, a recurrent network. And so the output of that network is to predict the whole sequence, and that's why we translate this into sequence data using a little trick. And basically, we're kind of checking for every sequence. We also think of a sequence as being promising, meaning having a positive label in that sequence training data, if only a subset of that sequence is part of another sequence that led to feasibility in a mathematical program. I'm not going to explain the equation here. The equation expresses this. So it also labels subsequences as positive if they are a subsequence of some other successful sequences that ended up with feasible mathematical programs. And now, how does the predictor actually work? So the predictor takes in, well, scene problem information, like a scene description and also goal description. And the goal description is actually given by this part here, and the, in a sense, like the action, so the action sequence is kind of given by this one here. And then the recurrent neural networks for that action sequence outputs like a discriminative value of how good actually that sequence is matching. Now, an important thing is that the way of how we encode like the goal and the scene, well, the scene itself is just being encoded by the depth image or the image, direct image. The goal is actually a first order predicate. And so we separate the encoding of the predicate itself, which is just an imager, and the objects it refers to. So the objects that it refers to are being represented as image masks. So the object references are really encoded, given as input as an image to the thing. And also the same for the action. The actions are also literals composed of a discrete predicate and some object references. And all the object references are being taken as input to the neural network as masks. And this allows actually this network to really generalize over objects and apply the same kind of reasoning across objects with multiple objects. Okay, I'm not going to go into more detail here. Visit the paper, Danny is going to present that. The results are quite amazing in the sense, let me first explain the right thing. And the scale here is the number of nonlinear mathematical programs that need to be solved. So how many, if a robot is in a scene and needs to solve it, how many mathematical programs that is tests of paths or so does it actually have to compute? How many logic searches? And for short sequences, it only needs like tiny little, right? And only when the sequence gets a bit longer, it has to solve maybe 6 or 7 mathematical problems, which is so much less than hundreds of mathematical problems that if you would have to do without that. I think I get the number in a second here. And also in terms of the time, it's just really a lot faster actually. And also in terms of the action length or the total time spent or so, it's just orders of magnitude actually better than if we would not have used that heuristic. I think that's the same plot again. I think I mixed up plots again. Sorry about that. Anyhow, so Danny's gonna like present a paper at RSS, paper number 3. Let me come to the discussion. Just 1 minute. So the title of this workshop is Action Representation for Robot Learning, which is a super interesting topic, of course. And the question is a bit from this perspective of sequential manipulation planning and TAMP, task and motion planning, what do we believe about how we should represent actions for robot learning? And I think like the first thing I would say is in full agreement to what Russ Hedrick yesterday actually in a workshop said, that we kind of would have to move on and try to do this kind of manipulation planning or TAMP, task and motion planning, with feedback controllers. And so I think the first step to actually get towards an answer of, from this perspective, what are the right action representations is to try to do exactly the same thing as I did, but not for paths, but actually for chaining feedback controllers. And that's actually very interesting. Russ Hedrick has this earlier work, of course, of QR trees and things like that. And it is really interesting to now think about how you could realize similar things in the context of TAMP and for a general reason. And I think this would be a really good answer, like what from the perspective of TAMP and these things that I just said, what are good action representations actually for learning? And my second comment for the discussion is actually the following. In a workshop abstract, you mention methods where that kind of combine learning with low-level analytical controllers. And I found this interesting. You kind of suggested that your perspective is that on the low level, we understand robotics. We can do analytic control also. On a high level, it might make sense to use reinforcement learning on top of these analytical controllers, right? I actually think about it quite much the other way around. I find it much more natural actually to think about like learning on a low level, for instance, actually having more realistic and robust controllers for pushing, for force-based manipulation, and combine that with high-level physical reasoning, which uses coarse abstractions and simplifications, as I did, and I think one has to do in order to actually generalize strongly and yeah, be able to plan over the longer horizons. So this is my actually second point for the discussion, that my perspective is much more that I would like to leverage learning within that framework, where we actually use high-level reasoning on abstract representations, but might leverage learning on the control level rather than the other way around. Okay, that's the end of my talk. Thanks for your attention. Thanks to the two, like Danny, a PhD student, and postdoc Chang-Su. This first paper is just accepted, and you find it in arXiv, and the other one is the RSS number 3. And there's also code development. Thanks.
Thank you, Marc.
We do have one question from the audience. So it's related to MPC being very different than motion planning or trajectory optimization. They are wondering if you could elaborate more on that, and what do you think are the fundamental differences?
Did I say that MPC is very different from motion planning and trajectory optimization? Oh no, what did I say?
What you said is that you would like to use MPC on top of the first work. That the idea is that if you have planning, then you can put the MPC and it should work, but actually you tried and it didn't work. I also have a question here about that, and I was wondering if it was because you said there are local minima. I guess that's the direction that the question is going.
Yeah. So yes. So the very often people, or it's kind of like a straightforward thought that if you can solve path optimization problems, that you can just make them short horizon path optimization problems and use that for model predictive control. And so this was, of course, also one of our things that we looked into. How could we actually do model predictive control for within our setting? And I think on a short horizon within one skeleton. So if within one mode, if we don't like leave that mode of interaction within that phase, let's say, that does make sense, and we could go that route. That's all fine. But we also looked into doing model predictive control when it actually might happen that the real execution switches the mode. So you accidentally actually could not like maintain contact, although your plan actually thought that you would maintain contact, and then you would suddenly have to do model predictive control also on the contact thing switching level, right? And let's say we were not good enough. Maybe Russ Tedrick did this actually with this perching thing, right? But let's say we were not really good enough to actually get this going, and we didn't really feel that this is I don't know, an easy way to move forward. Let's just leave it with that. Yeah.
Right. Okay. I think we have to move on to our next speaker. Thank you, Marc. We will have Marc also at the end on the panel discussion, so we can have more questions for him later.
Okay, thanks. Bye-bye.